Today we're going to move from emissions into the tropospheric gas phase chemistry lecture. And we're going to focus on NOx and VOCs because we're going to build up into the production of ozone in the next lecture. So in the first lecture, we talked a little bit about NOx and VOC emissions. So just to recap, NOx is dominated by anthropogenic emissions from energy and combustion, and this includes motor vehicles and industry. And there are also natural emissions of NOx, primarily from lightning, although there's also some that come in from the stratosphere. In terms of VOCs, which are volatile organic compounds, the anthropogenic emissions come from motor vehicles, the chemical industry, chemical manufacturing facilities, refineries, factories, etc. And there are, of course, also biogenic emissions of VOCs, and these primarily come from plants and trees on land as well as plants in the oceans. Before we go too far, I'm going to spend a couple of slides talking about concentrations and units and conversions, because you guys are going to have a series of practical questions that focus on NOx and ozone. So in terms of, there's a variety of concentration units we use in the atmosphere in atmospheric chemistry. The absolute concentration of something, which is the amount per unit volume, is generally given as the notation here with the brackets. So that says the concentration of X. There's also the mixing ratio, which is what I showed you, the gas concentrations yesterday of what's in the atmosphere. And that's mole per mole, or ppm or ppb, and that's denoted as a C for gas X. And then there's the number density, which is another type of concentration that's denoted as N sub X, and the units are molecules per centimeter cubed. And so that's the number of molecules of a gas, in this case gas X, per unit volume of air. And so the mixing ratio is useful because it doesn't depend on density at all and doesn't change as a function of altitude. Whereas the number density is useful when you're working with reaction rates as well as optical properties, but it's the reaction rates that we're going to find it useful for the practical question. And these two concentrations can be interconverted, they're related. So mixing ratio and number density are related by the ideal gas law. So the number density for gas X is equal to the mixing ratio for gas X times the number density of air. And another way to write that is Avogadro's number times the pressure in the atmosphere divided by the ideal gas law constant times temperature times the concentration and mole fraction. And so you'll use this. I'll give you concentrations in mixing ratio and you'll have to convert them to the number density. A refresher, and I think I made a mistake in the first lecture in terms of concentration units, so I just want to go over this one more time. So mixing ratios, the CX, can be in ppm, ppb, ppt. So 1 ppb, if we look here, 1 part per billion, or ppbv of a gas, is the same as 1 nanomole per mole, which can be rewritten as 1 times 10 to the minus 9th moles per mole, which is also equal to 1 times 10 to the minus 9 molecules per molecules. And this is why it's also referred to as the mole fraction, as the molecular fraction, because it's the moles of gas per moles of air. And again, this is useful because it remains constant when air density changes. But it's essentially the equivalent of saying 2 ppm of gas means there are 2 moles of that gas for every 1 million moles of air. Goodness, that's supposed to say air. Apologies. Or 2 molecules of gas for every 1 million molecules of air. So if we think about this in terms of normal interglacial CO2 concentrations, you could say it's 280 ppm, or 280 micromole per mole, or 280 times 10 to the minus 6 mole per mole, or 280 times 10 to the minus 6 molecules of gas per molecule of air. And so in the prac question, I'll give you concentration as ppb, and you'll want to convert it to molecules of gas per molecule of air. The other useful unit in conversion we have to think about is the units of pressure. So the SI unit of pressure is actually the Pascal, but there are a lot of units of pressure, and some are more useful than others. And you can see here I've given you the equations to go back and forth between units of atmospheres, bar, millibar, and hectopascals. So mean atmospheric pressure at sea level in pascals, which is the SI unit, is 1.01325 times 10 to the 5 pascals. This is frequently referred to in hectopascals, which is 1013.25, and that's because hectopascals are equivalent to millibars. which is equal to 760 torus celsius, which is a unit we don't use very often, but that's related to millimeters of mercury and when we use barometers. And all of that is equal to 1 atmosphere, which obviously is the most useful unit of pressure. So again, in your prac, I'm going to give you pressure in 1 unit, and you're going to have to convert it to another unit so that you can do the interchange between number density and mixing ratio. Okay, back to the chemistry. So why are we talking about NOx and VOCs together? And we've introduced a little bit the idea of primary emissions of NOx and VOCs. But now we're going to move on to chemistry. So these things together in the atmosphere lead to the secondary formation of other species. And in this case, it's all about ozone. Ozone is central to the chemistry of the troposphere. It's one of the main components of photochemical smog, basically air pollution. And VOCs and NOx together are the major precursors of ozone. So we're going to start by talking about NOx itself and its photochemical cycle. And then we're going to move on to talking about CO and methane, because those are the main VOCs in the remote troposphere, and those are the main VOCs sort of absent human influence. And then we'll move on to talk about the influence of other VOCs and how that works with polluted atmospheres. But we need to take a minor segue to talk about atmospheric oxidants. So the main tropospheric oxidant is OH, or the hydroxyl radical. This is known as the scrubber of the atmosphere. So basically, anything that ends up in the atmosphere doesn't stay there forever. Some things have a fairly long lifetime, but most things that, from an atmospheric chemistry perspective or an air pollution perspective, they're reacting with the hydroxyl radical and moving on to some other species. So the hydroxyl radical oxidizes essentially all non-radical species in the atmosphere. You can see here I've shown you how carbon monoxide reacts with OH to form CO2 plus H, and methane reacts with OH to form CH3 plus H2O. There are other oxidants, nitrate radical and ozone being the other two main ones, but even of those big three, OH is the sort of dominant one. And so it has a very low concentration in the atmosphere, but a very high reactivity. So any given OH molecule is only around for about 1 second. So where does the OH come from? It's the same in the troposphere and the stratosphere. And so what ends up happening is you have ozone reacts with light. This H nu is a shorthand way to refer to light. And it leads to oxygen plus this O1D. This is an excited oxygen molecule. This O1D reacts with water to form 2OH. Okay, so this is happening constantly, and then as soon as the OH is formed, it goes on and reacts with something. So what does it look like when we look at concentrations of OH in the atmosphere? So these are a combination of model and satellite images, these maps, and on the left you can see the OH concentration at night, and then on the right is the OH concentration during the day. And so because OH is formed from light, you can see the scale of the nighttime. So the maximum, the darkest color here is 0.28 times 10 to the 6 molecules per centimeter cubed. But during the day, it's much, much higher than that, okay? And so, which makes sense because you have to have the light to form it. At night, if you have really high ozone and some other VOCs, there is a way to get OH, which is why the VOCs you're seeing leading to the OH formation at night is why you're seeing it over land, particularly over densely forested areas. So during the day, places where you have a lot of water and a lot of light are going to give you your maximum OH production. And so that's essentially what you can see along the equator and your subtropics, where you have the most water in the atmosphere and you have the most amount of UV radiation reaching the Earth. So that's where you got your maximum OH concentrations. Okay. So back to NOx chemistry. So why do we lump NO and NO2 together and refer to it as a chemical family known as NOx? And there's a couple of chemical families in the atmosphere where we do this. So the reason is that most NOx is emitted as NO, but during the daytime, there's really, really rapid cycling. I mean, sub-second rapid cycling between NO and NO2. And so the NO and NO2 are destroyed and reformed so fast that you almost instantly establish a steady state cycle. And this is known as the photochemical NOx cycle. And this is why I refer to it as the NOx family, because it's basically impossible to distinguish between the NO and NO2. So as soon as NO is emitted, it reacts with ozone to form NO2. So that's sort of this part of the arrow here, forms NO2. And then if there's light, NO2 immediately is photolyzed back to NO, and that's this reaction here. And this is all balanced by those oxygen molecules combining to form O plus O2 and ozone. So you don't have to worry too much about R2. But basically this cycle just keeps happening over and over and over and over and over. So it's much easier to just lump them together and call them NOx. And this concept of steady state I want to touch on for a second, because in the prac we're going to use this to calculate the concentrations of NO and NO2. So the steady state basically means that this reaction R1 is equal to R3. And so it's R1 is the destruction of NO2, and R3 is the production of NO2. And so steady state for NO2 is where the production and destruction is equal, which means R1 must be equal to R3. If we think about the steady state for NO, it's essentially the same but in reverse. So the destruction of NO happens during R3, and the production of NO happens during R1. So if NO is also in a steady state, then we have R3 equals R1, and you see essentially that's the same thing as that. So we can use this and some information about kinetics, and so we're going to have a quick bonus slide on kinetics. Bimolecular reactions, like the ones we were just looking at for NO and ozone, require the two things to come together and smack into each other. So A plus B must come together and actually interact to form C and D. And the rate of this reaction is essentially saying what's the loss of A as a function of the loss as a function of time, which is equal to the loss of B as a function of time, which is equal to the production of C as a function of time. Note the minus sign has fallen away here. Which is equal to the production of D as a function of time, which fundamentally the most useful part of this is that that's equal to the reaction rate constant K times the concentration of A times the concentration of B. And this K is a rate constant for a reaction that's determined in a laboratory. It's typically given for a reaction like this in units of centimeters cubed per molecule per second. And so you should recognize that in this case, the concentrations of A and B must be in the number density form. So molecules per centimeter cubed. For a photolysis reaction, which is how NO2 is lost, it's a little bit simpler. So photolysis reactions involve some sort of species interacting with light, with photons. And in that case, X plus the light gives you Y plus Z. And so the loss of X as a function of time is equal to the production of Y as a function of time, which is equal to the production Z of function of time, which is essentially equal to K, the rate constant, times the concentration of X. And in this case, K is in different units. It's in units of per second because it's a photolysis rate constant. So putting this all together, when you want to calculate the steady state concentration of something, so let's say we want the steady state concentration of NO2, we know that at steady state, the reaction of R1 must equal R3. And so the destruction of NO2, which is equal to K1 times NO2, must be equal to the production of NO2, which is equal to K3 times the concentration of NO times the concentration of ozone. So in a steady state, these two things must be equal. So you could set them equal to each other, and we'll do this in your prac. So you could say K1 times the concentration of NO2 must be equal to K3 times the concentration of NO times the concentration of ozone. So we'll use that equation in your prac to calculate some concentrations of NO and NO2. Okay. The other thing we can do with reactions R1 to R3 is calculate the steady state concentration of ozone. And this is known as the photostationary state relation. And in this case, this J value, don't worry too much about that. That's related to photons and sunshine, etc. But the point here is that the concentration of ozone, which tomorrow's lecture is going to focus on, is directly related to the ratio of NO2 to NO. All right, so it's not related to just one of the concentrations, but it's actually dependent on the ratio of NO2 to NO. And so this steady state ratio of NO to NO2 varies across the day because of the dependence on light. So at noon, when light is at its highest, your rate constant is going to be at its highest. And that's when NO is the largest possible fraction of NOx. So at noon, the ratio of NO to NO2 is about 0.32. But what about at night? So if you think about NOx at night, it's a little bit different, right? Because there's no light at night, which means this reaction can't happen, which means that you essentially have this reaction happening a lot. So any NO that's emitted becomes NO2, but then the rest of the cycle has broken down. So any NO that's emitted becomes NO2, becomes NO2. So at night, essentially the concentration of NOx is equal to the concentration of NO2 at night. Okay, so this NO to NO2 ratio varies a lot during the day because of this dependency on light. Okay, so that's NOx conversion. But eventually this NOx must go away, right? It has to be removed from the atmosphere. So during the day, this is your main loss process of NO2. It's oxidized by the OH radical. And remember I said pretty much everything is oxidized by the OH radical. M is an inert body. What this means is that M is just something that this reaction needs to bump into to make it happen. Usually M is equal to N2 gas, right? Because N2 gas is 78% of the atmosphere. And it's inert. So NO2 plus OH plus whatever it bumps into leads to the formation of nitric acid. And so at a typical OH concentration of 10 to the 6 molecules per centimeter cubed, which is what we saw in those satellite images, NOx or NO2 only sticks around in the atmosphere for about a day before it's removed. But NOx can also be removed at night. And remember, there's no OH at night because OH is formed from sunshine. And so at night, NO2 reacts with ozone to form the nitrate radical and oxygen. And then NO2 and the nitrate radical react together to form N2O5. And that N2O5 and water get together on an aerosol particle to form nitric acid. So this is the way you get rid of NOx at the daytime, and this is how you get rid of it at nighttime. So let's look at some satellite NOx concentrations, or NO2 concentrations in this case. Anything in red means it's potentially above 5. This is your color bar down here on the left. So in 2005, you can see this is from the OMI-R satellite, so this is total column values. You can see fairly high concentrations in the eastern part of the US. You see higher concentrations in Europe, China. We've got our local hotspot here in the Highveld. And then you can look and see in 2014 how things have changed. And so changes you might expect to see would be related to if certain countries have enacted air quality policies or tried to reduce emissions for various reasons. So you can see actually from 2005 to 2014, the US increased the stringency of its NOx reduction policies, and their NOx concentrations went down quite a bit, not just in the east, but also in the west around California. Concentrations in Europe have gone down a little bit. Concentrations in Asia, I think, look roughly the same, and I would say the sort of hotspot here also looks roughly the same to me, not that different. And if we zoom in, actually we have to change the units to look at, this is looking at the 2014 hotspot in the Highveld, and you can see it's actually quite a high spot because it goes all the way up to 10 now at this point. It really is quite high concentrations. Okay, so that's what NOx looks like sort of globally and locally. Let's move on to VOCs. What do they look like in the atmosphere, the other component of this chemistry? So in remote atmospheres, carbon monoxide and methane are the main VOCs present. They account for the large majority of the reduced gas flux to the atmosphere. And this top image is a satellite image of carbon monoxide observed from space. And you can see a lot of the sources are from forests in this case, as well as anthropogenic activities, much lower over the southern hemisphere. And the bottom map is methane observed from space. So methane is a little bit harder to observe, and so getting concentrations over the ocean is a little bit more challenging. But you can see here the methane concentrations. And remember, too, that methane is a greenhouse gas. So methane concentrations, if we look here, this is an interesting way to present them. It's a sort of 3D latitudinal look at methane. So warmer colors are higher concentrations. And what you're looking at here is a function of latitude in this direction. So higher concentrations in the northern hemisphere than the southern hemisphere. And then you're looking at this over time going this direction. And you can see it's going up over time because it's a greenhouse gas and those concentrations are increasing. So this is kind of a cool way to look at the hemisphere. But you also see there's a seasonality to methane. And that's because it's linked to biological activity. So in addition to CO and methane, there's also what we call non-methane VOC emissions. So these are all your other volatile organic compounds. The largest being from isoprene, which comes from vegetation, so isoprene, terpenes, and those things. You also get some from biomass burning, and these are slightly different. They're alkenes and aromatics, so they're all volatile organic compounds, but they're actually different compounds. And then industry also leads to a lot of alkenes, alkanes, and aromatics. Isoprene is an important VOC partly because it's the largest in terms of emissions. It's almost as high as methane. But it's also interesting because it oxidizes in the atmosphere with OH, remember, which everything oxidizes with. This is what isoprene looks like from a molecular perspective. And it forms really reactive products. So isoprene leads to formaldehyde, carbonyls, dicarbonyls, all sorts of things are formed from isoprene. And here's this is a pie chart looking at the global estimates of these, and you can see again isoprene, monoterpenes, and then other reactive emissions. And here, this is another way to look at the isoprene oxidation products, and it just sort of highlights the interesting chemistry that happens. So you have VOCs emitted that react with OH, and they go on to form organic peroxy radicals, which actually influences, this is our little NOx family that we're familiar with here. And they can go on to form all sorts of things. You see the products start to get more and more complicated as we go across, including forming aerosols. And we can observe some of these oxidation products from space. So we can observe formaldehyde and glyoxyl, two key isoprene oxidation products. And on the bottom here, you can see the map distribution. Isoprene comes from trees. So again, where you have lots of vegetation, you have lots of isoprene products. And here, glyoxyl, you can also see there's a strong signal over the ocean. This is actually sort of an active area of research as to why there's so much glyoxyl produced over these oceanic regions. And just a refresher that, of course, in order for NOx and VOCs to get together and do some chemistry, they have to last long enough to encounter one another. And so the lifetime of these species matters because that controls the transport, how far around the world it can be established. So from a vertical perspective, it takes 1 or 2 days for the boundary layer to mix. But if you want to mix higher up into the troposphere, you need to be around for at least a week or a month. And then if we look at horizontal transport, you can see, and this should be familiar to you guys because of the way the winds blow, that the fastest thing to do is sort of move on this direction with the winds. But even still, to go across from the US to all the way to China, you need to last in the atmosphere for about 2 weeks. And to be transported from the northern hemisphere to the southern hemisphere, you need to be around for almost a year. And that's partly to do with how the ITCZ is very difficult to get across. And so that's why some of these species, you see the concentrations are much higher in the northern hemisphere, because they just don't have a long enough lifetime to get down into the southern hemisphere. And all of this is going to come together in tomorrow's lecture when we talk about ozone, which is formed from the combination of NOx and VOCs. And there's good ozone and bad ozone, and we will talk about both.